I'm just double checking. All right, so we're live. Hello, everyone. Welcome to our GDG Seattle's meetup tonight. GDG Seattle is a fast-growing community with over 7,000 members, and we are an inclusive community where everyone is welcome to learn, practice, and share Google technology, services, and platforms. Our motto is be excellent to each other. If you see or experience anything different, please contact GDG Seattle organizers. So I'm Margaret. I'm the lead organizer of GDG Seattle. Tonight is a book launch event for the recently released O'Reilly book, Machine Learning Design Patterns. Let's welcome the authors of the book, Lak, Sara, and Mike, to share with us a few of these tried and proven methods to help you tackle problems that frequently crop up during your machine learning process. And first, I'd like to introduce Lak. And Lak is...
Hi, Margaret. Hello, everyone.
Yeah, hi. Yeah, Lak is the global head for data analytics and AI solutions on Google Cloud. His team builds software solutions for business problems using Google Cloud's data analytics and machine learning products. And please also welcome Sara. Sara is a developer advocate on the Google Cloud team focusing on machine learning. She inspires developers and data scientists to integrate machine learning through demos, online content, and events. And let's welcome Mike. Mike is a machine learning solutions engineer in Google Cloud. He helps customers design, implement, and deploy machine learning models and teaches the machine learning immersion program in Google's Advanced Solutions Lab. So tonight, we're going to have 3 talks by Sara, then Mike, and then Lak. Each talk is going to be 15 minutes long. Then afterwards, we'll have a Kahoot quiz, giving away 5 of the books. Then we will have Ask Me Anything, and so you can ask questions to the authors and the speakers. I have included the social media information here, everyone's Twitter handle, and then Mike has his LinkedIn information here. So if you, during this event, feel free to take pictures and post it on social media and reference his social media handles. So let's get started with the first talk by Sara.
Hey, everybody. Thanks, Margaret. And thank you to you and GDG Seattle for organizing. I'm going to go into present mode. I'm assuming everyone can see my screen. So hey, everybody. Welcome to our book launch event. Our book is called Machine Learning Design Patterns, written by me, Lak, and Mike. So we'll get started. First of all, what are design patterns? So design patterns are essentially repeatable solutions to commonly occurring problems. They can be applied to all aspects of software engineering. Obviously, here we're focused on design patterns specifically for machine learning. And our book is organized in different chapters that take you through the entire end-to-end machine learning process, from data pre-processing to training models to scalably deploying models in production. This is a diagram that is in the end of our book in a summary chapter and just highlights how all of these different patterns can work together. So we're each going to be giving you a sneak peek into one of the patterns in the book. So we're going to start with rebalancing that I'm going to cover. Then Mike is going to cover continuous evaluation, and I'll go, and then Lak will go over bridge schema. So with that, I'm going to get started with rebalancing. So all of the patterns in our book are organized in the same format, where we start out by presenting the problem that this pattern solves, a solution and an implementation of it, and then we end the chapter by talking about some trade-offs and alternatives. So I've organized this section in a similar way in this presentation. So starting out, the problem that this pattern is solving is that most real-world data sets are not perfectly balanced. So, maybe you've done, getting started tutorial where, let's say it's a multi-class classification problem, and each class has exactly 1,000 examples in that data set you're using in the guide. Unfortunately, data sets in the real world are almost often always not perfectly balanced. So this is an extreme example on the right of a fraud detection data set where less than 1% of the examples are from the fraudulent class. So we're most often dealing with data sets that have a different balance of data for each class. So this is often for anomaly detection problems, predicting a rare occurrence of an event, but it could also be for multi-class classification. So if you have more than 2 classes in the classification problem you're working with, often you won't have exactly the same amount of examples for each label in that. Just a quick note before I dive in. So bias is often a bad thing, but it's not always a bad thing. So what I'm referring to mostly when I talk about this entire pattern is what's called naturally occurring bias. So this is bias that you can't fix by collecting more data. So assuming that the data set you're working with encapsulates all the possible data and couldn't be improved with more data collection. Unfair bias, which we cover in a different pattern that we won't get into today. This is covered in the fairness pattern. This is when the data that you're working with doesn't accurately reflect the population that may be using your model. So we're focused on naturally occurring bias in this section. So the first thing that you can do when you have an imbalanced data set is you want to make sure that you're looking at the right evaluation metric to understand your model. So let's say that you choose overall model accuracy as your metric. This might not always paint the best picture of your model, especially when you're dealing with imbalanced data. So let's say you have an overall model accuracy of 93%. The same model, if you look closer at the accuracy by individual classes, you'll notice that this is pretty bad. So this is an example of a binary classification problem. When I say minority class, I'm just referring to the class of your data where you have fewer examples. So it looks like from this confusion matrix, we can see that our model is only classifying examples from our minority class correctly 12% of the time, which is pretty bad. Yet this still shows us overall model accuracy of 93%. So you want to make sure that you choose the right metrics to evaluate your model. Otherwise, you may not even uncover the issue that's occurring. So we focus on 3 methods in this section for handling imbalanced data, all part of the rebalancing pattern. Downsampling, upsampling, and weighted classes are the main solutions. So I'm going to give you a little preview into what each one looks like. So starting with this data set, let's just assume we're working with a binary classification problem. Focus mostly on tabular data here, but these techniques can be applied to other types of data as well. So let's say that this is the balance of your data. You have way more examples for your majority class. So with downsampling, what it suggests you do is discard a random sample of the examples from your majority class, and the resulting data set is much more balanced. Some caveats here: you want to make sure, let's say you're dealing with some time-focused data, you want to give some thought to how you're discarding those examples, because you probably want to discard an equal amount of examples across the time that your data set includes, rather than just, say, cutting off the first 1,000 from the beginning. So based on what your data looks like, you want to think about how you want to downsample. This approach is probably the simplest of the 3, but it obviously won't work if you don't have enough minority class examples to begin with. So a very extreme example, let's say you only had 100 examples in your minority class, downsampling probably wouldn't work, because then you'd be left with only a data set of maybe 200 to 300 total examples. So just something you want to be aware of with downsampling. So this would be the resulting data set that you're dealing with. So looking at upsampling, let's say we're starting with the same data set balance. This technique is a little bit more complex, but basically you do the reverse, hence the name. And you generate new data, synthetic data, based on the examples that you have for your minority class. There's a couple of ways you can do this, but there is a popular technique called SMOTE, which stands for Synthetic Minority Oversampling Technique. There's a great archive paper on it. Essentially what this paper proposes is that you take real examples from your minority class. Here we have just a sample data set that's predicting whether or not a patient has heart disease. So these are 2 real examples from the minority class. And using SMOTE, we would look at the feature space of these data points, and then we'd use that to generate a new data point from the same feature space. So in the example you see here, we've just taken the midpoint between these two values for each of our features to generate this synthetic data point. You could use a similar approach for image data sets using image augmentation. So if you only had a small number of images for a certain class, you could augment those images to generate more synthetic examples. Kind of a similar approach to what Smote proposes for tabular data. And then the third technique is weighted classes. So you can think of weighted classes as the minority class examples in your data set, if data sets could talk. It would be just saying, pay more attention to me, focus more on these examples. So with weighted classes, the approach is basically you want to tell your model when it's calculating the loss or error metric to assign more weight to examples from the minority class when it does that. And this is possible to implement in many different machine learning frameworks. We're showing Keras here. So the way that you determine what the weight should be is based on the balance of that class in your data set. So we calculate the data set balance, and then in this case, we just pass, Keras lets you pass a class weight parameter when you're training the model. I know XGBoost has similar, can also do it with BigQuery machine learning, lots of different ways to implement weighted classes. A note, since I've talked about 3 separate solutions, the cool thing about these is that you don't have to pick just one. You could, in fact, use all 3 together. So you could downsample your data a little bit, because when you're downsampling, you also want to be careful that you don't take away important information from the majority class. You don't want to lose information. So maybe you downsample a little bit. You also upsample, but your data set is still slightly imbalanced. So then you could also use weighted classes when you train your model. So that's the solution that we focus on in the solution section for this pattern. I'll just quickly touch on some alternative techniques. Just gonna see how I'm doing on time. All right, looking good. So reframing is actually a separate pattern in the book. I'll just touch on it briefly. What this approach suggests is that you take a problem that, let's say you had a regression problem predicting a numerical value. So in this chart, we have a data set of baby weight. And so let's say we're predicting the weight of a baby, the numerical value, but instead we see that our model isn't performing well on predicting outlier values. So we could reframe this into a classification problem where we could bucket the data instead, maybe into underweight, average weight, and overweight, and then see if our model does better using a bucketed classification approach. Other alternative approaches for handling imbalanced data sets, these are specifically related to anomaly detection. The first is you could use the error that you get on your predictions as a signal of whether or not something is an anomaly. This is obviously a more rare solution to use, but let's say that your model outputs a confidence score on new inputs. If the confidence score was very low, you might be able to use that as a signal that something was an anomaly. The second approach is to use a clustering model. And the code snippet on the right is how you would create a clustering model in BigQuery machine learning. And so a clustering model is an unsupervised learning approach, which means that you don't have to provide the labels when you train your model. So the model just splits your data into clusters, looks for trends in the data, in this case, 4 clusters. And then to identify anomalies, you could determine that an anomaly is something that doesn't fit well into any of the clusters. So in this example, this is just showing 2 different examples that we're sending to the model. So the first example on the top, this is predicting that our model would be in cluster number 4. We can see there's a pretty low distance between this data point and the data points in that cluster, which is a good sign that it fits in that cluster, so it's not an anomaly. This data point, for example, looks like it is an anomaly because it's pretty far from all of our clusters. So that's an alternative approach to dealing with imbalanced data. And then just to wrap up, a quick note on explainability and fairness. So if your data set is dealing with fairness considerations, then the rebalancing pattern is one possible solution, assuming that you have made sure that you have collected all the possible data that you can and that your data set accurately reflects the population. If you've done all that and you still see that the data set is heavily imbalanced, then the rebalancing pattern can be really helpful. And then another topic that's covered in a different pattern is explainability. So it's really important, especially in anomaly detection, to understand why your model predicted that something was an anomaly. So the example I'm using here is fraud detection. And so the graph that I'm showing on the right is showing which features were most important to our model in cases when the model flagged a transaction as fraudulent. In this case, it's really important to know why the model thinks a certain transaction is fraudulent. And we can see here that for each transaction, there were different features that caused the model to predict fraud. So a lot of our patterns are connected, as you'll see throughout our presentations. So this is just a quick note that you can use rebalancing hand in hand with fairness and explainability. So with that, I'm going to pass it over to Mike for continuous model evaluation.
Okay, great. Thanks a lot, Sarah. Okay, so I'm going to talk about continuous model evaluation. This is the 18th pattern in the book. So just to frame where continuous model evaluation lies. So continuous model evaluation falls in sort of later stages of the ML life cycle. So when you're working on some ML problem, it happens after the model has been deployed. And you can think of it as sitting in the broader concept of like model monitoring. So the idea is like you've gathered your data, you've done your data validation, you've cleaned your data, you've trained a model, it's excellent. You've deployed your model, it's doing really well. But then the world changes sort of around you and your excellent model is no longer doing so well. And the idea is you want to be able to track your model's performance over time so that you can recognize when that happens and you can fix your model or improve your model when it's no longer performant for its task. So in the next couple of slides, what I want to do is just give some examples as to like why this would happen and how this can happen. Talk about what continuous model evaluation looks like, so how you can use this to address this problem. And then, as Sarah mentioned, with this pattern, as with the other patterns, we'll discuss some like considerations and alternatives that you can have in mind if you want to employ this design pattern. Okay. So two of the main reasons, or two big reasons why models will become less performant over time are the notions of concept drift and data drift. So in concept drift, the idea of concept drift is that the underlying assumptions of your model have changed in some way. And this is actually a really common occurrence for models that are trained to learn like an adversary or a competitive behavior. Things like fraud detection models or spam filters or cybersecurity. And the reason why is that in these scenarios, you have a predictive model that's trying to identify patterns of a certain activity, of fraud detection, for example. And like while the model is learning to determine what's fraud, the adversary learns how to adapt and they'll modify their behaviors, which causes the data distributions to change, and then your model performs less well. So you can think of, as a specific example, you can think about credit card fraud detection and how the way people use credit cards has changed over time. So for example, when the chip and pin technology was introduced, a lot of fraudulent transactions started moving to be online, so it's much harder to commit fraud or have credit card fraud in person. And that causes the data to change. And so the models that you had developed to recognize fraud, they're no longer as good because the data has actually changed. Another example of concept drift is in text. So we'll see an example later of like text classification. And so the idea here is like the words themselves haven't changed. Like the word troll, stell, or cloud, like they haven't changed, but they've evolved over time to have a more digital meaning. So trolls can live under a bridge or they can be behind a computer screen, and a cell can refer to a jail cell or a mobile phone. And since the meaning of these words has changed over time, if you've changed some model, like it's an interpretation of those meanings or the features that are learned from those words will also change. And so your model can suffer. And then data drift. This refers to any change that has occurred in the data that you're using, you're feeding to your model for prediction, that anything that's changed from the data you used during training. So this can happen for a number of reasons. The input data schema could change. So where the data that's being fed to your model could change. Fields could be added or deleted that could harm your model. Feature distributions can change over time, or the meaning of the data changes, even if the structure or the schema hasn't. So maybe even a more recent example is this current pandemic. Here's an article from the MIT Tech Review. which is that Amazon saw these massive shifts in the type of orders that people were making during the pandemic. People were buying more in bulk. They were buying a lot of items related to the coronavirus. As this article points out, you don't just train a model and walk away and be done with it. You should really think about model deployment as a continual process. So how do you go about doing that? And it may seem really obvious, but what you need, the simplest way to put it, is that you need some way to compare your model predictions with the ground truth. And if you think about it, this is something you do during your model development. Like as you're training your model and exploring how good it is, you have your holdout, train, validation, and test sets. And right, you're training on your training data, but your validation data set exists so you can assess how well is your model performing on unseen data. So really the idea of continuous evaluation is just carrying over that practice into the deployment stage. So seeing how your model performs on unseen data, in this case, like new real-time examples. And the only way you can really do that is if you have a way of capturing your model, the requests for your model for predictions, your model predictions, and then you need to have some way to tie that back in with the actual ground truth. Okay. So as an example, to see how this actually works, and as Sarah mentioned, a lot of the patterns all the patterns we have in the book, they're paired with some code examples. So there's a GitHub repository for each of the patterns where we'll put into action some of the code that we use to implement these ideas. And so the code that we have for the continuous model evaluation is performs evaluation on a text classification model. So just to frame the problem a bit, we have a data set. It consists of a whole bunch of article titles, and the label is the source of the news article. So it's a multi-class label. Either the article comes from the New York Times, TechCrunch, or GitHub. So we train the model. Once we've trained the model, we can deploy to in this case, this is a code snippet what it looks like to deploy this model to Google Cloud. It's fairly straightforward. Here, just to call it a few things that we'll see in later slides, the model name is text classification, so TXT-CLS. And the next part of that snippet is saying, okay, we're going to deploy this model we trained locally. We're going to deploy a version v1 from this local directory. And that way we'll be able to serve our model for predictions via a REST API. So when a user sends a prediction, sends a request, in this case, asking for, what is the source of an article, the title, House Passes Sweeping Policing Bill, we want our model to, it'll choose between New York Times, TechCrunch, or GitHub. And when you set up a continuous evaluation job in Google Cloud, a proportion, and you can choose the proportion of those responses are saved to a table in BigQuery. So here's an example of what that table may look like. There are these fields. So it records the model name, which we saw before, the model version, the date time of when that request was sent, the raw data, in this case, just the text of the article title, and the confidence score for the model prediction. So, in this model that we build, it has a softmax layer at the end. This confidence then relates to the confidence of, in that example, the model predicting New York Times for that article. Okay. You can set up how many of your examples are saved for later evaluation, in case you want to do a lot or do a few. Okay. So then once these are saved in this table, the next step, of course, is to join that back with the ground truth label. So this can be done in a number of ways. So you can set up a human labeling service, or more likely what's going to happen is you'll have to go back and you look at those examples, and someone will provide the ground truth. So that last column that I left off was the ground truth. And this allows you to, at some later date, go back and look and see, okay, we have all of our inputs, we have all of our model predictions. How accurate were we over these various examples? Okay. So because this level of information is gathered, it gives you a chance to do lots of interesting analysis for your predictions. So for example, you're capturing the date time of when the requests were sent. And so this code snippet just shows how you can look at how your model performs over time. Right? The idea of this is we want to see how our model is doing over time. And so we can choose a time and then say, okay, now look at our model performance 1 week ago, 1 month ago, and we can really get an idea of how the performance is degrading, if it's degrading. So we can think of this as providing a framework to evaluate exclusively on new data. And we can, ideally what you've done is you set up a threshold beforehand, and you can see, okay, once the performance of my model dips below a certain amount, that's a signal to you that it's time to retrain the model. Collect new data. It could be a problem of data drift or concept drift, and then retrain the model to improve the performance. Another feature, another aspect that is captured in this continuous evaluation framework is the model version. And so this is really useful for doing like A/B testing of models, but also doing like a dark launch of a model to really see like how are these two models performing before you want to swap one out. Again, the idea is the same. Now what we can do is we can slice that data set that's being captured in BigQuery on either one of the versions, and then we can compare the performance between the two versions with new data that's arising, new requests that are coming in. So just to mention a couple of the considerations you might want to have in mind, it's important to mention, I said before, like you have to wait to be able to have ground truth to join it back to that table. And this is, makes sense, but also can take some time. Like you can think of an example where you've trained a model to predict customer churn. So if that's the case, you actually won't even know the label until like maybe many months in advance. Or if you are trying to predict like quarterly earnings or quarterly revenue, like that actually won't be a number that you can compare back until later. So it's saved, the data's there waiting for you in BigQuery, you can add it back later, but it may take some time to actually have the ground truth labels. Another thing to keep in mind is, like I mentioned before, is like you want to see when your performance start to dip below some threshold, and that will indicate to you that you might want to retrain. And so really this is like a trade-off, as many things are in machine learning and elsewhere, but where you set that threshold will determine when you want to retrain. And the kind of things you want to have in mind are, if you set your threshold too low, then obviously you're allowing your model performance to degrade perhaps too much. If you set the threshold too high, then you may find yourself wanting to, having a trigger to retrain your model over and over again. And of course, like these kind of performance metrics could be tied to some cloud function to kick off a job to retrain your model. And depending on what your use case is, how complex your data is, or how costly it is to retrain, that may be not advantageous to retrain so much. So that's the kind of the trade-off you want to have in mind in determining where to set a threshold. And just to wrap up, an alternative to continuous evaluation. So there's this framework or this infrastructure in place that you can, again, like just pair your model predictions with the later ground truth. Sort of like a cheap way of doing this, or a way you can mimic the continued model evaluation in an offline environment, is to try to get some a feeling for how much does your data change? Like how necessary is this for you? Like when should you be retraining? So if you look at the time axis and you're now, one way you can get a feeling for how your model will suffer with old data, if it's trained on old data, is to actually just, think about it like a time machine. You go back in time 6 months ago, pretend that's your universe, take that stale data, train the model on the stale data, do your evaluation on that stale data in that moment, and then use that model, bring it forward to the present day, take your new data, and evaluate your model on that new data. And then you can compare the evaluation metrics of that one model. If there's a big discrepancy in only that short amount of time, you want to look into better understand why. That's also an indication of how often it may be necessary for you to retrain your model to keep it performant. Okay, so that's it for continuous evaluation. I'll pass it off to Lack to do bridge schema.
Right, thanks. Thanks, Mike. Okay, and the third pattern that we want to talk about today, the 23rd pattern in the book, is bridged schema. So this comes even after the life cycle. You already have a model that's been deployed, but you've got to realize that whenever you train a machine learning model, you train it on data, and lots of times the input providers get better over time. So let's say that you've built a machine learning model to recommend the amount of a tip that someone needs to leave. And when you train the model, the payment type that you got from the device that someone uses to basically swipe, you basically got that it was either a cash payment or it was a card payment. But over time, right, a few months go by, maybe a couple years, and rather than just getting that it is a card payment, you now get the type of card. Is it a credit card? Is it a gift card? Or is it a debit card? So the data has gotten better over time. So the model is out there, you've trained it, you've deployed it, you're happy. And now a new input provider comes along, or an input provider themselves have improved the model. And at this point, of course, you say, I have better data. What do you want to do? You want to improve the model, obviously. But the problem is that all of your historical data only has cash versus card, right? It's only the new data that you're going to get that will have this new information of whether that card payment was a credit card or a gift card or a debit card. So the question is, how do you use this new information as quickly as possible? The thing to realize is that all of your new transactions, they have this new information in them. So your input provider has changed. So now you no longer get this, it's a cash or it's a card. Now you get which type of card it is. But you also know that when you trained your model, you used 1 million transactions, historical transactions, to train the model. Does that mean that you're going to be getting new data? You have to wait for 1 million examples of this new data before you retrain the model. That's painful. And you have to realize that when you have a machine learning model, you will have hundreds of inputs into that model, and every one of those inputs is going to improve over time. And so this idea of having to wait for new data with a new schema is problematic. So let's assume that we have 1 million transactions with the old schema that had only 2 categories, cash and card. But we have only 5,000 transactions with the new schema. So we've just started receiving it. We have a couple of days of transactions, and we say, how can I use this 5,000 transactions to improve my model? Can you do that? And that's basically the solution that the bridged schema is solving for you. So the basic idea is, first, you estimate the distribution. You have 5,000 new transactions that were paid with a card, and you look at the payment type of those 5,000 new transactions, and let's say that 60% of those transactions are credit cards, 10% are gift cards, and 30% are debit cards, right? So you have your distribution on the 5,000 new transactions that have been paid with a card. And then you basically now say, how about I do data augmentation? So the idea is you take your old examples, and if the type is cash, it's cash. You pass it through, it's still cash. But if the type in the old transaction, those 1 million transactions that you had, if the type is card, then what you do is you generate a random number and you treat it like throwing a dart at this pie chart. And depending on where the dart falls, you pick the card type. So 60% of the time, the card type is going to be credit card. 10% of the time, the card type is going to be a gift card, and so on. Right? So you basically throw a dart and you pick it. So that's the first approach. You basically do data augmentation using a probabilistic approach. But here's the idea. What are we assuming here? We're assuming that, right, we don't know what type of card was used. And so we're going to randomly assume that it's just, right, there is really no information content in here. So we're just going to randomly assume that it's going to follow this distribution. But imagine that you do this many times. What's going to happen? If you train this model long enough, then every row in the card, remember that you're going to iterate over this model for multiple epochs. So at one epoch, or 60% of the epochs, this transaction will be treated as a credit card. 30% of epochs, this transaction will be treated as a debit card. And 10% of epochs, it will be treated as a gift card. So every transaction then that is a card transaction, if you've gone through it many times, then on average, the 1-hot encoded value is going to be 0 for cash, 0.1 for the part of it that is a gift card, 0.3 for the part that's a debit card, and 0.6 for the part that is a credit card. So your one hot encoded value averages out to be the probabilities. So you really don't need to do data augmentation. You can actually just, instead of one hot encoding your data, replace your data by the probability distribution. Right? So that's a static approach, and that's how you bridge the schema. So, okay, there's a couple of questions though. How do we measure performance of this? If I bridge the schema, is it actually better? And secondly, when I'm doing this bridging of the schema, I'm taking the old examples, some of the old examples, and I'm basically converting them. Even though it only has 2 categories, I'm making it up to be 4 categories here. And then I'm basically going to be adding in my new examples, right? So, but how many old examples do I need? How many new examples do I need? How much should I augment with my old examples? So what you do is you need to first, right? The first question, how do we measure performance? The thing to realize is you need to measure performance only on the new transactions, right? From now on, you're always going to get the actual type of card. So you want to basically retain some of those transactions in order to measure performance. The question is how much, right? So you take your old data, your 1 million examples that you have, and you say, what if I use only 500 of them to evaluate? What if I use only 1,000 of them to evaluate? What if I use only 2,000 of them to evaluate? So you go ahead and you randomly sample, let's say you're doing 2,000, you randomly sample 2,000 of it each time, and you basically go ahead and you measure the performance. You basically get what that variability is. So what I'm plotting here is a standard deviation of the accuracy measure if I take 1,000 samples from my million examples and I use that for evaluation. And as you can see, the standard deviation basically drops. And by the time I get to about 2,000, 2,500 examples, I have a pretty good measure of how good my model performance is going to be. So bottom line, I need to retain 2,500 examples for evaluation, which means how many new examples do I have? I have 5,000 total. 2,500 I've kept aside. I need another 2,500. So I have 2,500 new examples. Now I need to basically go back and find how many old examples can I have. And again, we do the same thing. So what we do here is that we keep 2,500 new examples, and then we have 1 million old examples. Like we have enough old examples that we need. We start to take a few old examples, and then we basically train the model, and then we take some more old examples, we train the model again. And so here I'm taking 20,000 examples, 40,000 examples, 60,000 examples, and as I add in the old examples, I keep evaluating, right, how well the performance goes. And you can see again that it starts to saturate, so that by the time I get to about 60,000 old examples, I have enough. So bottom line, I'm going to take 2,500 new examples. I'm going to take 60,000 old examples, maybe. And then I'm going to take those examples, and then I'm going to augment them. I'm going to train my model. So that's the basic idea behind bridging. The idea behind the bridge schema is you take your old examples and you take your categorical variables and you replace them with a probability distribution. Rather than one hot encode it, you replace it with a new probability distribution. And then that's the way you bridge it to the new schema. You take the old data, you bridge it to the new schema, you retrain the model. This allows you to use all of these older examples in order to train the new data. You get your ML model in production faster. Okay, so that's what we suggest. What are some alternatives? Well, if you're used to your data warehousing approach, the way you would do this in data warehousing is that you would say, I'm going to keep all my old data as 2 categories and all my new data as 4 categories. That's called a union schema. That's not going to work here because all your evaluation data in production you are always going to get the new schema. You will never get the old schema in production because your input provider now gives you 4 categories. Okay, so union schema doesn't work. You need to bridge the schema. Another approach is another design pattern that we cover in the book called a cascade design pattern, which involves a cascade of models. You train on one ML model, and then you take the output of that ML model and you train the other one. So in this case, you would basically train a series of ML models, first with cash versus card, and then with the new data. In this case, it is too complex because remember that over time, we will actually come up with enough new examples where we can throw away this bridging. The bridging is a temporary workaround so that we can get to production faster. Okay? So it's not really worth building a separate new infrastructure. It's much easier to take your one-hot encoded values and replace them by floats. But that works if the feature is categorical. What if you have a numeric feature? How does it work? Right? So that's the last bit I want to talk about. So if you have different types of features, right? If the feature is numeric and it's normally distributed, then you replace that feature by the mean value of that feature. If the feature is numeric and it's skewed, then you basically use a median value. If the feature is categorical and it's sortable, again, don't do this. I showed you about categorical features and mutually exclusive. You replace with a probability distribution. If the feature is categorical and sortable, you want to use the median. If it's categorical, not sortable, use the mode. And if it's a Boolean feature, you replace it by the frequency of the feature of it being true. Again, we talk about why these are the right recommendations for these other types of data. But the point is, regardless of the type of data that you have, it is possible for you to train your model with just a few new values and by taking your old values and bridging them to be the new schema. Okay? So bottom line, the bridge schema is useful because when an input provider makes improvements to their data feed, it allows you to use as much of the newer data as you have available, but augment it with some of the older data. And this way you get to improve the model accuracy, get to use the newer data more quickly than waiting until you have this 1 million examples of the new schema, which now might delay you by many, many, many months. And that can be problematic, right? You want to go to market as quickly as possible. So in summary, right, Sara, Michael, and I, we showed you 3 of the design patterns from our book. Okay, and they're from different chapters. The rebalancing design pattern is from the chapter on problem representation, where the problem that we're trying to handle the heavily imbalanced data, and we showed you 3 solutions there: downsampling, upsampling, or using a weighted loss function, depending on different considerations. And many of you were familiar with downsampling when I looked at some of the YouTube comments, but the upsampling was actually pretty new. This idea of generating data it's kind of odd, right? Even with bridge schema, we are generating data, and by generating data that is new, it allows you to have these amazing new capabilities. So again, with upsampling, you are generating data using the SMOT method, and that can help you rebalance your data in a much nicer way without throwing away the data, which is what you would do when you do a downsampling. The second design pattern that we looked at was continued model evaluation. The idea is that whenever you deploy a model over time due to data drift and concept drift, the model performance drops. So you want to take a subsample of all of your predictions and store them in a data warehouse and then compare them later on with the ground truth when it becomes available. And then once you do that, you kind of monitor the performance. And when the performance drops below a certain number, you go back and you take all these ground truth observations, you add them back into your training data set, you retrain your model, and you move on. Right? You may retrain your model, you might fine-tune your model. There's multiple ways that you can do this, but bottom line is that you change your model in response to your model evaluation. And the third design pattern that we looked at from the chapter on reproducibility was this idea of bridge schema, which is that when new data becomes available, any changes to the data schema would prevent you from using both the new and old data for training. So the way that is you take your old data and you adapt it to match the schema of the new data so that you can train your model. And the three patterns that we looked at here, rebalancing, continued model evaluation, and bridge schema, the last chapter of the book talks about the relationships between patterns. So for example, rebalancing, when you're downsampling, you want to use all of the data. You don't want to throw away the data. One of the ways that you can do that is through an ensemble. So you can basically do this multiple times and each time pick a different part of the majority data set to keep. Okay, so rebalancing is often used in conjunction with ensembles. And rebalancing is often also used along with fairness criteria, as Sara mentioned, with explainable predictions. And also, it can be addressed by reframing as a classification problem, as we talked about, right? Similarly, continued model evaluation, you normally use it along with model versions. And whenever you do continued model evaluation, you should incorporate a fairness lens to make sure that you're catching the cases where your model starts to perform poorly for specific segments of the population, right? So that's one common reason to do continued model evaluation. Bridge schema is very related to hyperparameter tuning because we use hyperparameter tuning to decide how many of the older examples to use. It is also related to this design pattern called a feature store, which is a way of basically making sure that you're documenting versioning and features using in your bridge schema using a feature store. And with that, right, I'll leave this link here, give you a chance to take a photograph of it. There's a link to purchase the book. O'Reilly is offering a free trial for 30 days to read the book online. So that's the link to get that free trial for 30 days. Follow us on Twitter, lac_GCP, that's me. SRob tweets, that's Sara. And Michael, of course, is smart enough to not have a Twitter account, so you don't get to follow him. So he uses his time more wisely than we do, I guess. Read our blogs as well, Medium on Medium, and Sara has Sara Robinson.dev. And again, all of the design patterns, we have the code. It's in that GitHub repository, ml-design-patterns. And with that, we get to Kahoot time. So what we're going to do now is we're going to do a quick Kahoot quiz. The top 5 winners, right? Basically, make sure to take, if you win, make sure to go ahead and take a screenshot of your screen, of your mobile device, and send it to Margaret, and we will basically send you a copy of the book. Okay? So that's what the Kahoot quiz is about, about getting a copy of the book. And it's also, of course, fun. So we hope that all of you play. So let me go ahead and start the game. Okay, so we're going to get a game pin. All right. So join www.kahoot.it. And so you can do this from any phone or any web, any web browser. And then enter the game pin 6670073. All right, we have 2 people joined. 6, 9, 22, 23. Hooray. $48. Okay, let's wait until it reaches maybe 60 and then I will start it. And don't worry, go ahead and enter. The first question is doesn't have any points. It's a kind of cute giveaway, so it's okay. So again, www.kahoot.it with this game pin. The game pin is also in the YouTube comments. So once I change the screen, if you forget it, that's how you can get that. All right, 60. I'm going to start. 3, 2, 1. All right, so the first one is a poll. Are you ready? So all right, 30 people are ready. 4 people are like, hold on, my friend's joining the game. All right, let's give people 2 more minutes. Oh, no, not 2 minutes. 2 minutes is too long. 5, 10 seconds, and then we will go ahead and we'll start. Almost everybody is there. Okay. All right, ready for the real first question. In a bridge schema, you can use the blank design pattern to choose the number of old examples you need. "46, 53, 55. Come on, people. All right, 56 people got it. 16 people got it right. Hyperparameter tuning, that's right. That's the way that you get the number of old examples that you need, right? Absolutely. Okay, no problem. There are 9 more questions, so you're all okay, right? It's okay. Let's go ahead and go for the second question now. Okay. At this point, Manjula's leading Steve, Rag, Spencer, and Csaba. All right, next. Okay, quiz. To create baseline models for explainable predictions, you use the blank design pattern. Again, we did not cover this. So this is now, what do you know about ML design patterns beyond what we covered in this? So, all right, the correct answer is that you use a heuristic benchmark. Again, that's a design pattern that basically talks about what are some good, easy ML models that you can use to compare in order to basically see, is my model, the explainability of your model. Okay. So next question. So Sridhar is now in the lead, okay, and Martin is close by at number 2. Third question. To reuse transform between different ML tasks, consider the blank design pattern. All right, this one's hard. The feature store design pattern is a way to reuse the transforms between ML tasks. So I guess this is all saying that this book is going to be useful to a lot of people. Okay. And Steve's now in the lead, and Sridhar is still there, close by. Okay. Next, the blank design patterns are helpful if you want to do fine-tuning. There are 2 correct answers here. 2 correct answers. If you want to do fine-tuning, which design patterns do you need are helpful?
So feedback. Somebody said the timing is off. I know the live streaming has a little bit of lag.
Okay.
So perhaps we can give a few more seconds
Sure.
after each question. Thanks.
Okay. I see. Oh, okay. Yeah, it's set to be 30 seconds. I think it's I can't change it at this point. So next, that's a good thing to remember for next time. Okay. So correct answers are checkpoints and transfer learning. Okay. So still Steve in the lead. All right. To handle categorical features with an incomplete vocabulary, you can use the blank design pattern. This is the first design pattern in the book, hashed feature, which is super useful if you have categorical features that keep growing over time. If you have an incomplete vocabulary, user IDs, movie IDs, provider IDs, these are the kinds of things where you will always have incomplete vocabularies because you will hire new employees, you will have new doctors, etc. Hashed features are extremely useful. Okay, so first design pattern in the book. Steve, still in the lead. All right. In the rebalancing pattern, okay, back to our talk today, blank is an approach to handling inherently imbalanced data sets. All of the above. Hooray, all of you are listening. Awesome. Okay. So Steve's still in the lead. Okay. To ensure that your model performs well as data and external trends change, you can use blank. Continued model evaluation. Perfect. Okay. 9 of 10. So 2 questions more. This is it. Last but one. Feature crosses should be combined with a blank design pattern to avoid the curse of dimensionality. Embeddings. Yep, that was the most selected answer, and you are all right. Embedding is how you avoid the curse of dimensionality. You take something that's high dimension and you basically move it to a lower dimension. Great. Last question. And we have a new leader, Subarno, by 2 points. Wow. And it's okay. The top 4 have been, I recognize the names, Subarno, Steve, Danger Mouse, and Csaba. Let's see if they can keep it. Last question. This is for the marbles. When comparing model performance in continued model evaluation, it helps to use the blank design pattern. Mike covered this. Awesome. Again, a lot of you got it. Model versioning. You should use model versions whenever you're comparing. If you need to compare two models, you want to use that. So, who won? And the runners are for Sara and Manoj. So the 5 of you, Sara, Manoj, Csaba, Steve, and Subarno. Okay. So please go ahead and take a snapshot of your screen and contact Margaret. So contact Margaret so that you get a copy of the book. Congratulations. And now we move on to Q&A. All right. So Margaret.
Yes. So it's Q&A time. Well, someone said, how do you contact me? So I assume most of you are attending this through either Meetup or Eventbrite. So on Eventbrite, if you just contact organizer, you will get hold of me. And so now it's Q&A time. I am going to show the question. So I think right now, I'm going to remove the sharing, and perfect. I'm going to just put the question on the screen. And any of you can feel free to answer the question.
How much data is too little? I'm dealing with a situation of less than 100 positive examples among 500,000 negative examples. I guess this is about the rebalancing pattern. Okay. Sara, you want to take that?
I can take this one. Yeah, unfortunately, a lot of times the answer is it depends on the data you're dealing with. But you can still get something that works. We have a data set. There's one in BigQuery actually called ULB fraud detection. It's also on Kaggle if you search like credit card fraud detection. That one has a similar balance, though not as extreme as the situation you're dealing with. I would say in this case it's probably worth trying upsampling. There's usually not like a hard and fast rule on how much is too little, but I'd say, yeah, worth giving upsampling plus weighted classes a try, and seeing how that works. Anything to add, Lack or Mike?
Yeah, that's. Any other questions?
So I think earlier there was also questions during the talks and after each talks, but I guess Sara and Mike, you already addressed each of them through chat, right?
Mm-hmm.
So now we're just waiting for new questions.
All right.
Okay. Any other questions? Please feel free to put in the chat.
Okay. So Ekart says, I'm not sure of resampling methods. If the reality is imbalanced, then we shouldn't resample. Well, the issue here is that if you don't resample, your model will basically treat these very unique things as outliers and might just ignore them. And sometimes those outliers are very important. Think of a credit card fraud situation. You may have very few instances of fraud. That doesn't mean that you should always give out the loans, right? You need to basically catch the fraud. So even though reality is imbalanced, the very unique situation is important to catch. So you will know the task might be to find these things that are very, very uncommon. And it turns out that ML models don't work well if something is extremely rare and it can get easily ignored.
Yeah, it's also important if you're dealing with a fairness situation where the data doesn't accurately, reflect the population. In that case, it is important to use some of the rebalancing techniques to make sure that it does.
Okay. So, Mike, I think the next question by Nihar is for you. For continuous model evaluation, what can you do about the model quality until we capture enough results to compare with the ground truth? How do you improve the model in the meantime?
Well, so it sounds like you're saying, so you've trained your models deployed, and then you're maybe waiting to have the ground truth to add it back to your predictions. In this case, it's like, I don't know if you necessarily have a reason to think your model needs to be improved. Like, it's almost like you're waiting to get information back, and you don't really even know what the state of your model is until that ground truth has been recovered, right? So you're kind of where you were when you were developing your model, in that you have a data set, you've done your train, validation, and test split, and you've done all the best practices in developing your model. Unless I'm misunderstanding what the question's asking. That's sort of how
Okay.
How do I update ground truth if there's drift? Well, the idea is that there likely will be. I mean, maybe there will be drift, and the updating the ground truth is just you should think about updating the ground truth as just finally providing the label for those examples. So your data, when you're doing developments in a jar, like it's there, and you do your best to mimic what the real world looks like by using a holdout test set. And this is saying, okay, you've done all of that, and you've chosen your model, you've deployed it. There's going to be new examples coming along. The idea here is you just want to capture those examples and those predictions.
It's just that as time goes on, like, new examples come by and there is drift.
Yeah.
Okay. Christopher Bear, great idea for a book topic. What was your inspiration for the patterns included in the book? Any good ones that didn't make it?
I had the same question.
Thank you. Yes, I've been a big fan of design patterns ever since I read the book by the Gang of Four on object-oriented design patterns, because these are a great way to capture expert knowledge and what people know in the field. So that was the inspiration, really, that there has been a really good book that captured expert knowledge. Of course, what happens is over time, these patterns become part of the libraries, part of the frameworks that people use to, at this point, you don't even need to know about the object-oriented design patterns, because they're part of the way that we all do object-oriented programming today. And our hope is that the ML design patterns undergo that very same kind of evolution, where the things that you do through patterns today, they essentially become part of the underlying frameworks. They become the normal way that things get done. And so you may not even think about it as a pattern that you have to basically go ahead and apply. But at this point in time, these are techniques, these are ideas that you want to incorporate in your development, deployment process, etc. Any good ones that didn't make it? I don't know. I mean, the book is relatively new, so I'm sure that we will see patterns that come by, a few months, a few years as we observe them. But at this point, I think we got all the ones that we wanted, and we threw out all the ones that didn't make the cut.
Also related, I published a blog post today about the process behind writing the book. I'll post a link in the YouTube.
Yeah, absolutely. That's a great blog. If you're interested in, like, how does it become, how do you go through the process of writing a technical book, Sarah's blog is extremely good. Okay. In school, our professor's approach was to use more data or even similar data sets so they wouldn't break the independence assumption. Which design patterns are related to this area? That would be like data augmentation.
Or maybe transfer learning too.
Yeah, and transfer learning as well. So no, so that idea is actually underlies many of the design patterns in the book, right? So data augmentation is a basic technique, and it's part of, like, bridge schema, for example, is an example of data augmentation. Emacs is better than VI. Let's move on. Let's go to the next question.
The book does teach a few approaches for model deployment.
Yeah.
So we do touch on AI platform. We also touch on a few other ones.
Yeah. For outlier modeling, what resampling techniques do you recommend? So again, I think we talked about things like SMOT, for example. So there's there are a number of these techniques, and we do talk about them. But
for image data sets, I think Keras has one called image data augmentation. I forget the exact name of the class, but there's a few approaches if you're working with image data.
The design patterns in the book are state-of-the-art solutions or simple medium solutions. These are the most commonly used solutions, right? So we try to stay away from bleeding edge research. We looked for solutions that have been proven in practice.
Okay, so if you want to contact me, just send me an email via Eventbrite or Contact Organizer. So even if it doesn't allow you to attach screenshot, at least I will respond. You'll get my email address. Okay.
In bridge schema, do you keep on changing the probability values of the new data? Yes. Yeah. So again, this is bridge schema is very much a temporary workaround. So you might do it maybe 3 or 4 times during the course until you get enough data and you drop all of the old data. So, and each time you treat it, you go through this entire process, estimate the probability distribution, make the change, retrain the model, do the hyperparameter tuning, and then deploy it. So you would go through the entire process. So that starts with estimating the probability of the value of the data. Mike, you want to take that?
Yeah. Let's see. So we have, well, one thing we're planning on doing is in Google, I teach at the Advanced Solutions Lab, and we were going to be running some webinar series for these patterns. And I'm sure we can make that public, let people know about when those will be happening. Yeah, that comes to mind right away. We're looking for, and also I think there's something planned for January as well, right? Like January, was it 19th or 20th, Black? Do we have something?
Yeah, so yeah, there's another one by GDG New York, right? Build You. So that's sometime in January. But again, I think the ASL one, if you can post it, Mike.
Yeah, I will.
Yeah, absolutely.
Yeah, and also, you know, there could be other events similar to this one, but you might have other events that are on different topics, right? On different platforms. Feel free to let me know, and then I can cross-post to let our members know as well.
Exactly. And also follow Sara and me on Twitter. Like whenever we do a talk, we always publicize it. So you should, you will get like links to articles or links to talks that we do.
Great.
Mike, take this.
Let's see. Upsetting sounds like fabricating data per probability distribution. So perhaps BigQuery ML has the way to export one hot encode array. Is there anything else to represent old data moments of distribution? Let me think of this again. So
yeah, in BigQuery ML in this particular way, it's like everything is bundled in. So I don't think you can do something like a bridge schema there very easily.
Yeah.
So
it does have weighted classes.
Yeah,
if you want to.
If you do weighted classes, maybe that can handle the kind of upsampling you would do otherwise.
Mm-hmm. Yeah. Okay. So not sure. Next question. All right. I can't. It's just does not like the resampling design pattern. Okay. Next. Okay. Great stuff. Thank you. Thank you, Jaden.
Okay. Oops. I think someone was saying, when is Margaret's book coming out?
Margaret has a book.
I don't know if that's a joke or a real question. I'm not writing on any books at the moment. So.
Didn't you have a book on Android, Margaret?
No, I don't have books. I write a lot of blog posts.
Okay.
Oh, by the way, I'm the GDG Seattle lead organizer. I'm also a machine learning GDE. So I write a lot of sample apps and blog posts, and I also give talks on machine learning. But my area of expertise is more on implementing machine learning models on mobile and embedded.
Cool.
So is this more like a feedback or something?
Yeah, it is like a feedback. Like, let's go.
Okay. All right.
All right. I keep hearing that deep learning needs a lot more data than classical ML. However, deep learning did better than classical model by 25% increase in accuracy with only 25K rows of data set. Why? This one was actually a pretty small data set. Normally, when you hear deep learning needs more data, people are talking not about structured data, but about things like images or video or audio. That's what that tends to be in reference to, not structured data. Next. Okay. Yeah. Free text. Interesting. Okay. Did you do word encoding or transfer learning there? Maybe. All right. Yeah, it's tough.
Not sure. Okay. Someone said.
Thank you. Have a good evening.
Have
Thanks,
a good
Michael.
evening. Is there book cover?
It is.
I see. Okay. Here's a similar reference. I don't see a reference.
Implementing ML on mobile embedded. Yeah, see, getting book ideas, Margaret.
Yeah.
No, there are quite a few other books already on the mobile and the embedded. Oh, but I do want to mention, I am running a on-device machine learning study jam in January. So for those of you who are interested, for GDG Seattle. Okay. Yeah, definitely. Writing a book is a lot of effort.
Yeah, and that explains it. When you use Word2Vec, you're basically taking advantage of a whole bunch of unsupervised ML already. So it's not fair now to basically compare what a deep learning model or a structured model can do, because you're essentially doing transfer learning at that point. Yeah,
okay, so I think I don't see any other questions, but I think even if there are more questions, I think we should follow up offline or connect on social media, because I think we've been answering questions for about 20-25 minutes, which is great.
Absolutely. And we're getting close to the hour. So
yeah, so
yeah, find us on Twitter, LinkedIn.
Yeah,
if you have questions.
for coming.
We're happy to answer.
Right. Thank you all for coming. This was a lot of fun.
Yeah, I wanna thank all of you, Sara, Mike, and Lak, for speaking and answering the questions. I want to thank the support of O'Reilly Media and Google Cloud. I also want to thank these groups for cross-posting, Seattle Deep Learning, TensorFlow Northwest, GEG Cloud Portland, and Google Developer Student Clubs of University of Washington and across North America, ASL Alumni Group, and many other groups I might have missed here. So it is so great to have so many people joining us tonight, and I'm looking forward to seeing you all at our next GDG Seattle event, and hopefully we'll have these speakers back.
Next GDG Seattle, hopefully in person. Thank you very much, Margaret. It was great of you to go host this and organize this for us.
Yeah.
ASL alumni.
Oh, Malaysia ASL alumni too. Oh, wow.
Oh, really? Oh, yeah.
That was like January this year. I was in Malaysia, and that was my last trip. I feel now like very constrained.
Oh, that's right. I think I saw you there during that session.
Yeah, this has been a great event, and thank you, everybody, and good night.
Good night.
Thanks everyone.
Bye.
Thank you.
Good night.
Bye-bye.